Okay, today I am going to prove the hook length formula. First, some notation. We will be using Cauchy's formula for the Schur function. That's in terms of certain determinants, and this notation is for those determinants. So if you have any integer vector, by this I mean a vector whose coordinates are all non-negative integers, then let's say then I'll introduce this determinant a subscript, let's call this alpha, a subscript alpha to be the determinant x1 to the power alpha 1, x2 to the power alpha 1, xn to the power alpha 1, x1 to the power alpha 2, x2 to the power alpha 2, xn to the power alpha 2, and so on, x1 to the power alpha n, x2 to the power alpha n, xn to the power alpha n. Right, so it's a generalization of the Vandermonde. If you take delta to be the vector n minus 1, n minus 2 down to 1, then A delta is the Vandermonde determinant, which is the product of I less than j, xi minus xj. Right. Now,
You mean the last one is 0?
oh yeah, thank you. The last one here should be 0. It's an n vector. That's very important. And Cauchy gave a formula for Schur functions. Well, actually he defined them like this. Which they were called Schur functions later on, but I think they've appeared in Cauchy's work before. Schur showed their connections with the representations of GLN. So for each partition, let's say that lambda is a partition of n, then for each partition of n, the Schur function a s lambda is a lambda plus delta by a delta. You can just take this as a definition, and it's not very difficult to check that this is actually a polynomial, and it's symmetric in the variables x1, x2, xn, because both the numerator and denominator, being determinants, are anti-symmetric in the variables x1 to xn. If you interchange two variables, you will be interchanging two rows of this determinant. So the numerator will change sign and the denominator will change sign. So the quotient will not change sign at all. So that's a symmetric function. Now, now suppose you have a function f which you can expand in terms of Schur functions. Okay, so there's a theorem which says that all symmetric functions can be expanded in this way. Oh yeah, so this partition lambda here is lambda 1, lambda n. Let's just assume it has n parts. You can add zeros to the end of your partition. It's a partition of n, but we'll add as many zeros to make it have n parts. It can't have more than n parts anyway. And lambda plus delta therefore is lambda 1 plus n minus 1, lambda 2 plus n minus 2, all the way to lambda n plus 0.
When you take a partition, you take lambda 1 greater than or equal to lambda 2 and so on.
So here lambda 1 is greater than or equal to lambda 2 and so on. And here we will have that these are in strictly decreasing order because you are adding numbers which are in strictly decreasing order. Okay, so now Now I'm going to describe a way to read off these coefficients from the expansion. So what you can do is you just write F A delta. Now by this formula you get this is lambda C lambda A lambda plus delta. Okay. Now I want to somehow from here read off C lambda. And let's just look at this determinant in order to do that. So what is this A lambda plus delta? I'll just do it around here. A lambda plus delta is the sum over all permutations in Sn, sign of the permutation, it's plus or minus 1, and then x1 to the which f is some symmetric function which is which I've written as a linear combination of Schur functions.
What is C lambda?
These are the coefficients. So these are just elements in your field, and these are the Schur functions themselves. So this is just a linear combination of Schur functions.
No, but I thought this is a bounded degree and that.
Yeah, so maybe I'll sum over, let's say, all partitions of degree n. Then this would be a homogeneous polynomial of degree n, and every homogeneous polynomial of degree n has an expansion in terms of Schur functions. So this is that expansion. Yeah, let's say this is a homogeneous symmetric polynomial of degree n, and suppose you can, so then you can always write it as a linear combination of Schur functions where lambda runs over all partitions of n, and we want to find a, write this as a sum of over permutations. And what should I put here? Lambda w1 plus n minus w1 x2 to the lambda w2 plus n minus w2 and so on, right. So it's a sum of these monomials. Now these powers here are permutations of this original set of powers. So there's only one monomial where the power of x1 is strictly greater than the power of x2, which is strictly greater than the power of x3 in this sum, because the moment you do any non-trivial permutation here, you will have at least one place where this will be out of order, it will not be decreasing, right. So there's exactly one monomial in the sum which has strictly decreasing powers of that, the power of x1 is strictly greater than the power of x2, which is strictly greater than the power of x3. So I'll call that a strictly decreasing monomial. This has exactly one strictly decreasing monomial. And what is that monomial? That monomial is what I'll call x to the power lambda plus delta, which just means x1 to the power lambda 1 plus delta 1, x2 to the power lambda 2 plus delta 2, and so on. So that tells you how to read off coefficients of strictly decreasing monomials from here. So so the coefficient of, so let's ask what is the coefficient of x raised to lambda plus delta in f a delta. Well, this is a strictly decreasing monomial. So it and each of these terms has only one strictly decreasing monomial, and there's only one term with the strictly decreasing monomial x to the power lambda plus delta. So this is equal to C lambda. Right? So you can extract the coefficients in the expansion of something as a linear combination of Schur functions by multiplying it by the Vandermonde determinant and looking at the coefficient of a certain strictly decreasing monomial. So that's a trick, and this trick together with formula for expanding power sum symmetric functions in terms of Schur functions will give us what is called the Frobenius character formula. So that other expansion is called the Monahan Nakayama rule. Let me just remind you about this. I won't prove this here, it's been proved in some of my earlier lectures which are online. Anyway, it's a standard result. So let me just remind you firstly what is a power sum symmetric function. So you define Pn to be, well, let's say Pk to be x1 to the k plus x2 to the k plus xn to the power k. And you define for a partition mu, suppose you have a partition mu which is mu1, mu2 and so on, then you define P mu to be P mu1, P mu2, P mu, well, okay, so just the product of these things. So just a product of these kinds of polynomials. That's called the power sum symmetric function corresponding to the partition mu. If mu is a partition of n, then this will be homogeneous of degree n. And the Monahan Nakayama rule is an expansion of this in terms of Schur functions. Says that P mu is equal to summation sum over all. So let mu be a partition of n, then this is a sum over all partitions of n of the character of the representation of Sn indexed by the partition lambda evaluated at a conjugacy class indexed by mu. This conjugacy class consists of those partitions whose cycle decomposition has shape mu. So that's the Monahan Nakayama rule. In this lecture we are just going to take this as a black box, I am not going to prove it. Okay, but I hope at least the statement is clear. These are the power sum symmetric functions. You try to expand them in terms of Schur functions and the coefficients turn out to be the character values of the symmetric group. So if you put this together with the earlier result about reading off C lambdas from F, it gives us a nice formula for reading off the character values of the symmetric group from certain symmetric functions, and that's called the Frobenius character formula. What does the Frobenius character formula say? It says that the value of the lambdath irreducible representation of Sn at the muth conjugacy class is equal to the coefficient of x, the strictly decreasing monomial x to the lambda plus delta in P mu A delta. Just follows from what I have said before. And now I am going to show how to use this character formula to get what's called the hook length formula, which gives the dimension of the lambdath irreducible representation of the symmetric group, or what is the same thing, the number of standard Young tableau of shape lambda. Okay, this is not a combinatorial proof, it's using all the representation theory of symmetric groups. There are combinatorial proofs as well. Here lambda, everything is a partition of n, lambda is a partition of n, mu is a partition of n.
So that sum is over lambda partitions of n.
So here this sum is over lambda partitions.
What happens if you were to change the rule of lambda and mu there? So you look at I mu of lambda conjugacy class S lambda. Does that happen?
Well, so the transpose of the character table is probably related to its inverse by some simple manipulation.
You're not getting some nice symmetric, special kind of symmetric function on the left hand side.
Oh, I don't know. Okay, so that's the Frobenius character formula. Okay, now let's come to the so we want to just compute the value of this character at the identity element of the symmetric group. So we want to compute dimension of V lambda, which is equal to chi lambda at what is the cycle decomposition of the identity? It's just 1 to 1 1 1 1 n times. So what we get is, we'll call that f lambda. It's the number of standard Young tableau of shape lambda. So what we get is f lambda is equal to coefficient of x to the power lambda plus delta in x1 plus xn to the power n e delta. So we just need to do this. We just need to compute the coefficient of f lambda in or coefficient of x to the lambda plus delta in this polynomial. This is the Vandermonde determinant. If you want, just remind you, this is a polynomial in n variables, alternating polynomial, and this is just you can expand it using a multinomial expansion. Right. So that's the program that we have. Frobenius actually gave a nice expression for this calculation, which I will do on the way to getting the hook length formula. So I'll call that the Frobenius dimension formula. The Frobenius dimension formula. This says that f lambda is equal to n factorial over product I goes from 1 to n lambda I plus n minus I factorial, and then the Vandermonde determinant A delta evaluated at certain integers, basically lambda plus delta. That's the Frobenius dimension formula. So we want to deduce this from what we just wrote down, that this is actually the coefficient of the monomial x to the lambda plus delta in the product of x1 plus x2 plus xn to the power n A delta. Yeah, it needs to be proved, it's not obvious. So we want to deduce this from this, and it's not obvious at all. In fact, the argument I am going to give, Vishwanath helped me to sort it out. So you could try taking derivatives, which is what I tried at first, and you could just do it somewhat more directly. So let's do that.
That quotient n factored by that is clearly the lambda plus x lambda plus delta quotient in the quantity.
Yeah. So here we are seeing an n factorial, and here we are seeing some product of factorials. So that looks like a multinomial expansion, except that these things don't quite add up to n, they add up to n plus n choose 2. So this is not, yeah, so there's some more stuff going on. So this is a very nice calculation. Let's just start with this polynomial x1 plus x2 plus xn to the power n, and then I have a delta x1 xn. Well, I can expand it out and I can write it as firstly sum over all alpha, where alpha will be running over all vectors with non-negative integer coefficients whose entries add up to n. This is from the multinomial expansion of this thing, n factorial over alpha. Well, let me just I'll also be expanding out this determinant, so that will give me a sum over all permutations w in Sn. And what should I put here? So I'll have this multinomial coefficient n factorial over alpha 1 factorial dot 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 up to alpha n factorial, and then I'll have the sign, and then I'll have x1 to the right. So I'll have x1 to the power yeah, so here I'll have x1 to the power alpha 1, x2 to the power alpha 2, and there I'll have just this is a delta, so alpha 1 plus delta w1, that's just w1 minus 1, x2 alpha 2 plus delta w2 xn alpha n plus delta wn. No, so here wi is I minus 1, delta wi is wi minus 1. So these will be between range from 0 to n minus 1, but now they are all scrambled up. That's what we want. And what is the coefficient of x to the lambda plus delta in this? So if we want the coefficient of x to the lambda plus delta, we just need to pick out those summands here where these things are, this is lambda 1 plus delta 1, this is lambda 2 plus delta 2, and so on. So the coefficient of x to the lambda plus delta in this is sum over all alpha. Now there will be a restriction on this alpha, sum over all w in Sn, and then you will have n factorial over alpha 1 factorial, alpha n factorial, and then you just have epsilon w, and now the sum is over those alpha Of course, the alphas need to be non-negative integers and they need to add up to n, but you also need to have that alpha I plus delta wi is equal to lambda I plus delta I, only those ones. Okay. Yeah, I guess so, yeah. I mean, well, we'll think about that. Okay, no, so now, yes, I'm going to pull out a factor out of a hat. This is actually a factor that comes up in the hook length formula, which I perhaps should have stated earlier. But, so you take this thing and it's a sum over this weird set. There are these constraints, and then there's the non-negativity constraints for the alpha i's as well. And what you do is you multiply and divide this by a certain factor, multiply and divide by product I goes from 1 to n, lambda I plus delta I factorial. This is a factor that appears in the denominator of the hook length formula. So we'll introduce it here. But the nice thing about this is that when we see what cancellations occur between these things and these things, we get nice expressions which then will allow us to interpret things in terms of hook lengths.
Constraint on both alphas and W's.
Right, this is a constraint on alphas and W's, and in fact once you know what W is, it completely determines what alpha is and vice versa. So this is really a sum over one of them where the other is determined by it. If you know W, then you know alpha, because you can solve alpha is lambda I plus delta I minus delta Wi. And if you know alpha, you also know W, but not every alpha will give you a permutation. Okay, so let's put in this factor up there and down there. So I get f lambda is equal to
What's the reason for this?
yeah, so how do I explain where this factor comes from? It's only because this is what appears in the hook length formula. I don't have a good explanation for that. So I should have probably written down the hook length formula at the beginning of the lecture and then
Something comes in the determinant form at this specified.
yeah. Oh yeah, so sorry, this is actually just this factor.
That's there. Once
Yeah.
you know that,
Yeah, not even in the hook, it comes up right here in the Frobenius
but
dimension.
know that f lambda is this, then
Right, so once you know this, you know to multiply and divide by that. This formula actually appears in one of Frobenius's papers. We can look it up. So what you get is this n factorial divided by product lambda I plus delta I factorial, then summation alpha, summation W in Sn, and let me make some more space here. What do I want? I want to put this back in the numerator. Of course, I have this epsilon W, and then I have product I goes from 1 to n, lambda I plus delta I factorial, and we must not forget, well, I've already taken the product here, our old friends alpha I factorial. Okay, now that's a different a ratio of factorials, and hopefully we can just divide it and take the thing. So, beg your pardon?
When you were in factorial.
So I can write this as
you're saying the change in alpha.
yeah. As I mentioned earlier, this alpha and W determine each other, but then there's this horrible condition that all the alphas need to be non-negative, and so it's not so easy to just substitute one in the other. If you substitute out, solving for alpha in terms of W, then you'll have to add the additional clause that this thing should be taken as 0 whenever the alphas are negative, one of the alphas. They are not all non-negative. But now if you write it as a ratio of factorials, you can write this as a product of a string of numbers. So lambda I plus delta I times lambda I plus delta I minus 1 all the way down to lambda I plus delta I.
Alpha to be negative will take 0.
Exactly, plus 1. So now this reminds me of the riddle in school, you know, what is a minus x times b minus x times c minus x all the way up to z minus x, and the answer is 0. So that's what's happening here. If so, this last number is really just alpha I plus 1. I have just used this identity here, that alpha I is lambda I plus delta I minus delta wi. So if alpha is negative, then at least one of these terms will be 0, and this gives 0. So now I no longer have to worry about the non-negativity of the alpha i's, and now I can just solve for alpha in terms of w. So so in fact I have eliminated the alpha i's here, and I can just remove this. So that's there's a product over i's here which I had forgotten to write earlier. And is that okay? So now I want to bring this down to the Vandermonde determinant. So here's what we'll do. If you define fj of x to be the polynomial x times x minus 1, you take j factors, so x minus j plus 1. So that's a monic polynomial in x of degree j. And what we really have here is that f lambda is equal to n factorial product lambda I plus delta I factorial sum over w in Sn. And this thing looks like a determinant, epsilon w, and then we have product f delta w I of lambda I plus delta I, right, and I goes from 1 to n. That's what we have. And that's clearly a determinant, right? It's an alternating sum of something. So what are the entries of that matrix? Oh, I shouldn't have erased that. So that is really determinant of the matrix whose fn minus 1 x1 fn minus 1 x2 fn minus 1 xn fn minus 2 x1 fn minus 2 x2 fn minus 2 xn all the way up to f0, which is the constant one. Where you evaluate this at xi equals lambda I plus delta I. So you just want to take this thing and evaluate it at xi equals lambda I plus delta I. But look at this. This is constant 1. The next column is linear monic. Second column is quadratic monic, and so on. So you can easily reduce this to the Vandermonde. What do? This is monic of degree n minus 1. So you can just subtract appropriate multiples of these later columns and make this x to the power n minus 1. So you column reduce. Is that clear? To x1 to the n minus 1, x2 to the n minus 1. And then when you plug in xi to be lambda I plus delta I, you get precisely A delta of x1 plus delta 1, x2 plus delta 2, xn plus delta n. So that's just the Frobenius dimension formula. That the dimension of V lambda, or the number of standard Young tabular shape lambda, is it should have a product, right?
You mean lambda 1 and lambda 2.
Yeah, this should be lambda 1, lambda 2, lambda n, and yeah, that's it. There's no product now because no, I need to substitute here. What I did was I had f of this thing lambda I plus delta I. So I just it's just psychologically easier to think of it as a polynomial in x. So I need to substitute for xi lambda I plus delta I. So in here I need to substitute for xi lambda I plus delta I. So this with the x's it will just be the Vandermonde determinant, but I'm substituting in the Vandermonde determinant lambda 1 plus delta 1, lambda 2 plus delta 2, and that's exactly what the Frobenius dimension formula said. So now we'll just need to do one last thing, which is see how to go from the Frobenius dimension formula to the hook length formula. And that's a combinatorial property, combinatorial argument. So let me firstly tell you what are hook lengths and so on. Okay, so given a box in a Young diagram, you can talk about its hook length. Let me just draw a Young diagram for you. So let's say, so that has 6 boxes in the first row, 5 boxes in the second row, 3 boxes in the third row, and 3 boxes in the fourth row. So this is the Young diagram for lambda equals 6, 5, 3, 3. Now this is a partition of 17, right? So we want to use our usual convention of having as many parts as n, then we'd have to append a bunch of zeros at the end of this, 13 zeros. Okay, but let's not worry about that for the moment. Let's just, so there's some 0, I mean anyway there will be 0 boxes here, the picture remains the same. Now what is the hook length of a box? So let's just take this box here. Its hook length is all the boxes which I've indicated here. So all the boxes, that box itself, all the boxes which are to its right, and all the boxes which are below it. That's the hook length. So let me just fill out all these boxes with their hook lengths just to illustrate. So what's the hook length here? So there's 6 over here, and then this partition has 4 non-zero parts. So it's 6 plus 4, but I'm counting this twice. So it's 6 plus 4 minus 1. So that's like lambda 1 plus, so suppose I write lambda now to be lambda 1, lambda L, where lambda L is greater than 0. Then it's lambda 1 plus L minus 1. So anyway, here I get 6 plus 4 minus 1, so that's 9. Now if I go from here to here, I only lose, this arm becomes shorter, but this remains the same. So it only goes down by 1. And when I go from here to here, it goes down by 1. But now there's a jump, because this vertical arm has also become shorter. The horizontal arm always reduces by length 1, but now the vertical arm has become shorter. And how much shorter has it become? By 2. So the numbers 6 and 5 get skipped. Otherwise this is pretty much going like a factorial. And now I get, so 9, 8, 7, 6, 5 are skipped. I get 4. Then here there's no this thing 3. And then 2 gets skipped for this missing box. And I get 1. Okay. Let's do it with the second row. So here it's almost as if I'm just starting afresh. I just look at this 5, 3, 3. So it would start off with lambda 2 plus L minus 2. And then there'll be some missed numbers. So anyway, so this will be 7. I'm going to take a partiality to rows over columns. I'm going to do it along rows. You could have done it along columns. So I'm not going to say that this 7 is 9 with 8 in between skipped because there's one box. I'll just do it along rows. So that's lambda 2 plus L minus 2, that's 7. Here there's no skip, so I get 6. Here I get 5. Now here there's a skip by 2, so 5, 4, 3, 2, 1. And then here it is, well, okay, so now 1, 2, 3, 4, 3, 2, 3, 2, 1. Those are the hook lengths. So what's the skipping business? So what we are saying is that if I compute the product of the hook lengths, it's like a product of these factorials, but there are some numbers which are skipped. So I need to divide by them. So so product of hook lengths equals product over I of lambda I plus L minus I factorial and then I need to divide by all the missing guys. Now notice that the missing, the skipped things, each skipped thing corresponds to row that is a row in this diagram. See here this, there were 2 numbers skipped going from 7 to 4, that's because I took 2 rows ended at that column. And here there's 1 number skipped because 1 row ended at this column. So for each row there's a number that's skipped. And you need to figure out what is that number that's getting skipped for each row. Okay. And for this it's all the rows that are subsequent that come below this row. For this the skippings are because of rows which come after it. So it's like a product over I strictly less than j. So for each row subsequent to the row in which you're writing the hook lengths, numbers get skipped. And what is the number that gets skipped? It is, so you're starting with, so you need to just think this through a bit. So you're starting with lambda L plus L minus 1, but if you're in the ith row, you're starting with lambda L plus L minus I minus 1. And what matters is sort of the relative, the difference of lambda lambda L plus L minus I, lambda L plus L minus J. So for the, if I'm writing down the hook lengths in the ith row, the number that's skipped because of the jth row which lies below I is precisely this difference, lambda L plus L minus I minus lambda L plus L minus J. Let's just look at the first row here, okay, and for subsequent rows it's the same thing, you just you know, because you can pretend you're starting off with a partition with fewer rows, so it's enough to really understand the first row. So you're starting off with lambda L plus L minus 1, and then we're going to see the number skipped relative to that. So you're starting with lambda, so for the first row you have lambda L plus L minus 1. And then you keep going down, lambda L plus L minus 1, lambda L plus L minus 2, lambda L plus L minus 3, lambda L plus L minus 4 gets skipped because this row has ended.
So here lambda L plus L minus 1 minus lambda L plus L minus 2.
Oh, this is not lambda L, this is lambda I and this is lambda J. Okay, so you're starting with lambda L plus L minus 1, and the number that gets skipped here, the first number that gets skipped here is lambda 4 plus L minus 4, because lambda 4 is 3. Okay, and then the next number also gets skipped, lambda 3, which is also 3, plus L minus 5. So those two numbers get skipped. So these are the numbers which get skipped, which come in the denominator, and these are the factorials. Now look at this. This is a Vandermonde determinant right here. This is just equal to, this is just equal to this. This denominator here is just this Vandermonde determinant, because it's the product over I less than j, xi minus xj, where for xi I substitute lambda I plus L minus I.
No, L cancels from I.
Yeah, lambda I minus. So you could put, I want to actually put n, so there's actually still more discrepancy. I can put n here. So I also want to say that suppose instead of I had a 0 this thing here, then I would start with, I would try to have I would like to put 10 here, but the 10 gets skipped itself, so there's some skipping right at the beginning. So you start off with lambda I plus n minus I, but then you skip the first few numbers till you come to the first non-zero row. So what I want to say here is that it doesn't really matter. I can introduce more zeros at the end of my Young tableau and change these L's to N's, in fact. So you can change this to an N, you can change this also to an N. So it's the same thing because of the skipping right in the beginning before even you start, when you write down your very first hook length. And this really is this Vandermonde determinant, this denominator here. So now if you just compare this product of the hook lengths with the Frobenius dimension formula, which I'll just write down up here to remind you. We had n factorial over product of these things, a delta lambda 1 plus delta 1 lambda 2 plus. Then you get, just using this, this over this is the product of the hook lengths. So you get this beautiful formula, n factorial times product over the hook length. So for each ij will denote the coordinates of a box in the Young diagram, which is in the ith row and jth column, count, hij. And that's the hook length formula. The number of standard Young tableau of shape lambda is n factorial divided by the product of the hook lengths in the standard Young tableau of shape lambda. That's it.